Thanks again, Anders, and welcome to my session. This is a session about what's new in C++ Builder XE3 64-bit compiler. And we're going to pay particular attention today on the new language standard, C++ 11. So I'd like to share with you just a couple of features in C++ 11 that I particularly like. Actually, a lot has been added to the standard, so you can spend a lot of time investigating some of these new features. Now you have a compliant compiler to play with, so you certainly can try out pretty much any of these features and see what they do and how you can add them to your code in the future to get the best or the most out of this new language standard. Some of you, maybe not a lot of you, but some of you may be asking, what is C++ 11? What is this designation? It refers to the year in which a standard was ratified for C++, and it's really a shorthand name. The long name, which I'll show you in a moment, is not something you'd probably keep in your head very long. But in short, C++, the language, is part of an ANSI ISO standard. Same goes for C. And what that means is that there is a standards body, two of them, that have particular methods for allowing a committee to specify what is the standard. The way it basically works is that there's a group of participants, and these are folks that go to meetings twice a year to talk about things that should be added to C++ or things that should be removed, or anything that has to do with the language and what eventually will become known as the standard. This group is known as the working group, and a working group is specified each time they're working toward a particular standard. So the feature requests are brought forward to the committee, and this is in the form of basically proposals where they would ask, hey, we'd like to add this feature to the language, or we think this is something that needs to be fixed in C or C++. Those features are then tracked as issues, kind of like defect tracking. And during these committee meetings, these papers are discussed. Yeah, basically the committee is broken into two subgroups, and one is focused specifically on the language, and the other is focused on libraries. And I've had the opportunity to participate in a few of these standards meetings. It's a very democratic process. Yesterday we had the father, creator of C++ speaking about making C++ a standard, and even as the creator of C++, he has the same vote count as everybody else. Of course, he's a very influential person with regard to his beliefs and positions, but he gets one vote just like everyone else who's a voting member of the standards committee. So a very democratic process in that regard. And it's really active discussion, whether it's a language feature or something that's added to the library. There's always going to be lively discussion, if you will. Probably the liveliest discussion, which was a surprise to me, but thinking back on it, it makes a lot more sense now. It was around syntax. So oftentimes the group would agree on a particular semantic change, but would argue for hours on what the syntax should look like. So thinking back on it, syntax is important. Syntax can make a feature more usable or not, make it more confusing or more obvious, or be a total turnoff. There's certain languages out there that, for me, are fairly good languages, but for some reason the syntax is something that I just can't get over, and I think that a lot of programmers are like that. So syntax is surprisingly a hot topic in these standards meetings. Let me give you an example of basically just to show you all this information is kept online in the C++ Standards Committee website. So it's openstandard.org, and this is Working Group 21, which is the C++ Standards Committee. And all the notes are kept, and these notes go actually pretty far back into the past, as long as the working groups have been around. In 1998, let's go back to the slides real quick. in 1998, the first standard was published. And there's been 4 essentially standards in quotes published since then, with C++ 11 being the current standard. And again, the shorthand name is C++ 11 because it was ratified in the year 2011. Back in the early part of the decade, when I was participating in some of these meetings, we had called this this upcoming spec C++ 0x. And the expectation from the committee at the time was, we're definitely going to get this ratified before 2010. Well, you know, things take time, and it was ultimately ratified last year in 2011. So the 4 specs were the first spec for C++ was published in 1998, and the long name is 14882:1998. The informal name is C++ 98. And in 2003, another spec was published. This was kind of a bug fix release in 2003. In 2007, a technical report was published, and this dealt primarily with standard libraries. And in 2011, of course, is the current specification, which the informal name is C++ 11. So just to give you a quick example of how the committee works, I'll share with you a paper that when I was at Portland, we had published and brought forward to the committee. At the time, we were looking to add some of our standard extensions into the language, the things that we've added to C++ to make it usable for rapid application development and visual development environments. So if you look at 2002, the meeting happened to be in Santa Cruz, which is very close to where our home offices are and were, and we submitted this paper. One of our compiler engineers at the time, John Wigley, published the paper called PME, Property, Methods, and Events. So you can click on the actual paper, and you can see the write-up that we did. So this talked about why we built the PME model, and essentially to support modern GUI frameworks and visual development, and the features, the language features that we specifically built to support property methods and events, such as binding pointers to members and event handling and property syntax, as well as and with our proposed syntax as well. Again, remember, syntax is a hot topic within the ANSI Standard Committee, and the open discussion about things like RTTI, which are all things that we built into the language, our standard extensions to make it usable with the Delphi language and with VCL and FireMonkey frameworks. So sometimes things are accepted, sometimes they're not. Some of these notions were accepted, but the syntax is different. Some things were left to the vendor, if you will. C++ can't solve everything. And again, since it's trial by committee, it takes time to get things ratified and discussed and understood, and the ramifications of accepting something means compiler vendors have to live with it for a long time. So do developers. So sometimes things get added and then removed. Sometimes things get added, but in a different way, different syntax. So, for example, we had talked about binding pointers to functions. Well, that ultimately made it into the spec in C++ 11 as a Lambda expression. That's quite different than how we envisioned it back in 2002, but it is ultimately that same feature. So this is kind of a fun way to just explore a little bit about the specs over the years and some of the things that people had tried to solve and the discussions that went on during the committee meetings. Okay, so let's head back to the slides here. So just to kind of go through some of the specs over the years. So the first specification ISO ANSI standard was C++ 98. And this is when C++ really became a standard. Of course, features like templates and multiple inheritance were around long before the standard. The Object Windows library, for example, took advantage of these features well before the standard was published. And things like exceptions and namespaces, these were all part of what OWL how they implemented C++, but they weren't part of the standard yet. Of course, we all have a future view of the standard because these things are discussed many years in advance. But a couple of the key things done in C++ 98, of course, templates, generic programming was added in the language, multiple inheritance, namespaces, typecast, etc., as well as a library specification. And what was interesting about C++ 98 and this library specification was the use of templates. So just like any language, you have an RTL, your basic functionality that you're able to call into outside of the language. These are the libraries. And they tend to provide pretty basic machine-level access, such as file I/O or memory management or various other capabilities, usually some types, intrinsic types, or in the case of the STL, standard template library, container types. So container types were basically implementations of common data structures that every programmer uses, but implemented using templates. So that, for instance, if you wanted to have a array of information using the template, since it was implementing generic programming, you would use the same interface to create a vector of ints as you would to create a vector of strings or a vector of any type. So this container is a generic container meant to hold any data type that you like, and you just specify it when you create it. And then on top of those containers, standard algorithms. So it's pretty common with lists and arrays, for example, that you may want to sort them. So an array of contiguous array, like a vector, versus a linked list are completely different implementations in terms of how they manage the contents and how they manage those in memory. But a sort function does the same thing on both of them, which is to order the list in some way, either reverse or in some type of order based on your comparator. So this was a really interesting way to explore or provide good examples of C++ generic programming as part of a standard library to developers. A couple other things that were a big part of that, iterators were a very important part of this, because iterators were how you generically moved through a container. So you would create for loops that would use these iterators to be able to understand where the beginning and the end of the container is, and to iterate through that container and to provide a variable with which you can get your indexed content depending on where you are in that for loop. So the three of these together were pretty key and a big part of generic programming in C++. A couple other things that were added were string types, as well as streams. And streams were a mechanism to insert and extract information. So this was a one way, for example, that console I/O was done, as well as file I/O. You used a couple operators called the stream insertion and extraction operator. You could overload these operators for your own classes and use the same syntax as a standard stream to create your own version of insertion or extraction, either into files or into memory, etc. So a very complete library that demonstrated and provided, again, a lot of functionality around the standard language in 1998. So during those years, a couple other standards were released. In 2003, there was a bug fix basically for implementers like Borland or Microsoft or others. There was no change to the specification, though, so it was really considered, again, quotes, bug fix. In 2007, a library-focused release was made called TR1 and added a bunch of features as a technical report, meaning they weren't part of the specification yet, but they were earmarked to become part of the specification. So things like regular expressions, smart pointers, random number generators, et cetera, were again earmarked to become part of the specification when it was actually published, so that people can start using them with knowledge or with the assurance that this will be part of the specification in the future. And so why, really, why is the specification important? Well, there's lots of operating systems out there. There's lots of different compilers. C++ is meant to be a portable language. And the portability is really dependent on how well the standard is supported. So if you're using a feature in, say, GCC, and you want to use that same feature in, say, Apple's Clang-based compiler, well, your expectation would be that they support that same feature. And if they don't, then your code is less portable. So it's important for compiler vendors and C++ compilers to support the specification so that you can assure that you have portable code, that you can take advantage of the latest features, and so that you can also be able to use the latest versions of C++ libraries out there. So last year, C++ 11 was published, and as you can see, there was a lot of features added to the language. This is just a sample of the features that were added. So there's plenty of time to explore all these features, and now you have a C++ 11 compliant compiler available to you to explore many of these features. So this is, I find it personally very fun to say, hey, how does alias template work, and try it out in the compiler and get a good feeling for how I may be able to add it to something that I'm working on, which may add either to the readability or usability of my code over time. And talking about the spec wouldn't be complete without talking about the Boost libraries. So Boost, even though it's not part of the specification, is actually an extremely important library for C++ development. Almost every single C++ developer out there uses Boost, and Boost has a huge amount of functionality available through it. What's interesting in the tie-in to the standard with Boost is that most new C++ features, either while they're being presented to the committee for future inclusion or consideration, really, or they just have usefulness, and it's an open source project, so they get added into Boost. And to some extent, the committee looks at Boost to see, well, what's being used, what's being adopted out there in terms of features. So a couple of examples, we talked about Lambda expression binding a little earlier. Well, that feature existed in Boost for a long time, Boost bind. It actually, bind itself made it into the standards part of the library, but there's also language support for binding as well. Another example is the range for loop, which got added to the spec. So there's language syntax that implements essentially a for each loop. So a couple of examples of how Boost really adds or drives, if you will, the adoption of certain features and eventual inclusion of that feature into either the language or the standard. So let's take a quick look at some C++ 11 code inside the C++ Builder XE3 environment. This is a piece of code that was actually provided by a longtime friend of C++ Builder and former product manager Alistair Meredith. He's definitely one of the top C++ guys that I know, and is very interested in C++ 11, of course, because he's part of the committee and part of the team that put together this specification. So he put together a piece of code that tests, if you will, almost every feature in C++ language in a very succinct piece of code. So a couple of things to point out here is that here's where really most of the magic is happening, and what's being tested in here, for instance, is variadic templates, ability to add variable number of arguments to a template class. This is new in C++ 11. The ranged for loop and type ID, which are used, and auto, which are all used to infer data types and create variables based on those data types. A Lambda expression. Oh, and this also includes, by the way, a parameter pack, which how basically variadic templates work, as well as a Lambda expression, which is used to, as a closure in this case, to pull in arguments from the local scope and use it within an anonymous function right there in the project. So, he was very pleased to see that we were able to build this no problem, and very good assurance that C++ 11 language features are going to be well supported in the product. So I thought it'd be, there's so many features to talk about in C++ 11, and there's a lot of really good information out there on Yarna's Strustrup's page. You can find information on third-party pages. There's a great Wikipedia site called CPP Reference that I would highly recommend checking out. Talks about the features, gives code examples, etc. So I can't get into all of them in 45 minutes. So what I thought I'd do is I would talk about my top 10 features in no particular order. So kind of like David Letterman, except the order has really no bearing on reality. Furthermore, the order changes all the time for me because I'm exploring new features all the time. Some things I'll find and I really like, and as I'm playing more and more with the C++11 language, there's things that I find that I'm like, how did I live without this feature, for example? So it may or may not be represented in this list, and doesn't mean that I don't think it's important, but there's just a lot of features, and this is now you got a compiler to go and play with all these and check these out and start integrating these into your actual code. So let's go through a few examples. One of the things that I use a lot, because I like to play with simulations and math and graphics, and so random numbers are pretty important for that type of application. And in C, setting up a random number is a little complicated, setting up a seed and then generating those random numbers. Well, in C++11, a pretty complete random number implementation has been provided, and it's basically three parts. You have the random number engine, so this is the part of the spec that creates the random number, so it does the seeding for you and the generation of the random number, or the seeding really. You have the ability to create a distribution, so this is based on statistics, things like normal distributions, for example. And then you have the generator, and this is what actually brings back a random number. So if you're creating a random number distribution, you basically would create an engine type. You would create a distribution type. So in this case, I want a normal distribution events, and I'm going to use this default engine that I created to generate that. And then I'm going to bind the two together. And I use auto here, for example, to create this type called variate generator, which expects an engine and a distribution as its argument types. And once I have that set up, then I basically call the function, which is created from the variate generator, to provide me a random number. Additionally, just to make it easier, C++11 has provided basically one that does all three in one called random engine. You just create this random engine RE, and you call its function RE overloaded parentheses operators, and that will generate a random number for you and deliver that back to you. So number 9 for me right now is binding and functions. So binding is the ability to take a function and produce a function object. And one thing I want to point out, by the way, is that some of these are library features and some of these are language features. In this case, these are both library features. But this is how, in the previous example, we were binding the number generator, the random engine to the distribution, and creating a function out of that we use to we invoke using that parentheses operator. So bind is used to create a function object, and then function, this function object now is a type that can be invoked using those parentheses operators, and of course implemented to do pretty much anything you want with those parentheses operators. So that's how you saw that previous example of creating a random distribution. Another really interesting one for me in particular, because again I do a lot of 3D kind of graphic stuff for fun, is tuple. And tuples are used in a lot of places. They're basically just sequence of values that are paired together. So a couple of examples like we just saw in the binding example. This is how functions and binding work. This is how they hold arguments for that particular feature. But another really common example would be coordinate systems. So in 3D space, you have an XYZ. You can create a tuple of doubles to basically manage those. Or you can create your own types, of course, too, but tuples provided as basically a really easy way to create these types of value sequences. Variadic templates is actually a really useful feature. I mean, variable functions have always been useful, and in previous to C++11, there's no way to do that with template functions, which are used quite a bit. So this is the way to add variable arguments to a template function. And basically the way it works is you use this ... operator to create a parameter pack. And so what it's saying is, hey, this template has a variable number of arguments. It's all captured in this type args. You create a type of args. So I created a variable there, and then I use this for ranged loop, which you'll find later, and type ID to one, determine the type that I need, and to create for me the proper type of iterator so that I can pull the information out of that parameter pack and use it in my call. So for the for loop will iterate through that type for me, and then I just call into that parameter pack to pull out those types, or the members of that type. Probably one of the cooler, at least syntax-wise, features of C++11 is the Lambda expression, and lambdas have been around for a long time in calculus and in other languages as well. And again, some of these features have been alive and well in Boost for many years, but it's basically a mechanism to create anonymous functions, closures, functors, those kinds of things. The basic syntax is, and this is for closure in particular, is it uses capture semantics. So you have an operator called the capture device or capture operators, and these are shown in the square brackets. And this is what this is how you start a Lambda expression, and you're basically saying, I want to capture these types from the local scope that I'm in. You can capture by reference, and you would use an ampersand operator, for example, in there. You then specify the arguments to that function. You have an optional return type, which is specified by the arrow operator and the type, and then the body of the function. And I say the return type is optional because, again, C++11 has done a very good job of being able to infer return types. So let's say, for instance, you're doing a sort operation, and which expects a comparison function. Well, you can just use an anonymous function in there to do that. And by using a comparison operator like less than or greater than, it knows that a return type is a bool. So you don't have to specify that return type in that case. So you've seen this keyword auto being used quite a bit now, and this is a big new feature in C++11. Basically, auto is used to infer the variable type based on whatever is being assigned to that variable. Where I find this most useful, and you've seen this already several times in things like ranged for loops, but where I find it useful is when you have very long template types. So in the past, for example, if you wanted to iterate through a container class, you would have to create a forward iterator or a particular type of iterator, random access iterator, for example. So you'd have to know, first of all, what type of iterator you want. Then you'd have to know what type you're operating on. So you have to specify that to the template type when you create the variable, and then, of course, get that assignment back from the container. Well, now I can just use the auto keyword, and it infers all this information for me, and is much easier to use. I don't have to have all this foreknowledge. I don't have to rely on the compiler to keep me honest, if you will. It gives me the types that I need, and there's standard ways to use it. So, for example, one really common way to use this is in the new ranged for loop. So in this case, it knows how to operate on all STL containers, basically any container type that has a beginning and an end. And it will create for me. I use auto to create that iterator type. I use the colon operator to specify, hey, this is a loop that's going to operate on this container. And it does a couple things. It creates the iterator type for me. It figures out what the beginning and the end of this iterator is, and then it starts iterating through it. And for each index or each step through the for loop, it provides a dereferenced variable for me to work with. So it's very easy to use and a nice addition to the language. Here's a feature that's been added that actually is a removal. And this is one that I'm actually personally pretty happy with. In 1998, the very first spec provided a mechanism to export templates. And what this meant was, so template classes, since they're templates, need to be compiled or made aware to the compiler at compile time. And basically what this did was it went through a preprocessor type of step where it would expand the template for the type that was being used. So let's say you had a vector you were using of type T, and then you create a vector in your code of type int. So the compiler would need to generate all that code or type int. And that means it would have to go look up in the header file the implementation for that particular, it had to replace basically everywhere there was a T with type int. And it was difficult for the compiler without 2 passes to go figure out all the code that it would need to generate for that particular type. So that's how basically templates work. And export was provided as a way essentially for implementers, if they wanted to hide a template definition. The problem that they thought they were trying to fix was that vendors wanted to keep implementations hidden for various reasons. Maybe there was intellectual property, or there was other reasons to keep it hidden. But provide the definition in the header file like a typical function, and then provide the definition in the source file. So they, this seems like a good idea at the time, right? But it was really a nightmare to implement and support, and it took years for Borland, for example, to implement this feature. And it turned out that no one used it. Now, it could be that no one used it because it took a long time to get implemented by compiler vendors, or they just didn't see the usefulness of it. So this was a huge waste of effort for a feature that just never got used. And you really couldn't call yourself an ANSI compliant compiler without all the features, right? So this was, again, something that we at Borland had spent a lot of effort on. It was a nightmare, again, to implement support, and really had no market value, if you will, at the end of the day. So that for me was a big one to remove. And I like standards that don't just keep things around forever. They say, hey, this is not working, this isn't important, let's remove it from the standard. So this was removed in C++11. Now I could go into many different types that were added. Regular expressions were added, all sorts of stuff. One of the ones that I use a lot too is hash tables, which are just basically unordered containers, many different ways to set up hash tables. These can be used for all sorts of things, usually used for things like parsing, file sets, very common to use in, the very early stages of compiler parsing, for example. But this is just a simple way to create key value pairs. And so what you're seeing here actually is something I'm going to talk about is my current number one, which is uniform initialization syntax. And that is the ability to create, and especially for STL containers, initializing that variable with data without having to go through a loop to populate it. And so in the past, actually, first of all, there's many different ways to initialize variables and different syntaxes available for non-container types. For container types, there really wasn't a way. You had to sit there and loop through it using functions like insert or pushback, for example, to populate that container class. So now there's a common syntax, and where it's really useful is for STL containers. I can just use the parentheses operator and specify the types, and it's really simple. And one of the outcomes of this is out now. You can use the syntax to initialize member variables as well. So it feels complete in this regard to me, in the sense that it's uniform and that it's very common to initialize variables in your class as well. So having all this come together kind of completes the language for me at this stage. So for some of you, this may seem like a very minor feature to be my number one at the time. For me, it was actually something that was really annoying for many years, and it's nice to see a solution to it. So this, again, my list changes all the time, and the more I play with different features, this list is going to be constantly evolving for me. I'm the kind of person that likes to keep lists, so I'm always thinking in that regard. But just a couple of examples of things available to you in the C++11 language to play with. So C++ by itself, C++11 is a very complete language, and a very complete set of functionality as well, but it doesn't do everything. And that's why we have application frameworks like VCL and FireMonkey, where we can implement things like UIs, user interfaces, and we can implement things like data access layers and all the other things that the application stack takes care of for you. But it's common that we may want to mix and match these things. So I just created a real quick example using some of these features of a random number generator and sorter. using the VCL. And the basic idea here is we talked about random number generators. I use that random engine to generate a list of 10,000 random numbers. And then I sort those. And I use the standard sort function that we talked about against that container class. And so let's just generate the numbers here real quick. And let's sort them. Okay, so very trivial example, I know. But let's take a look at the source code real quick. So in my VCL application, I'm calling into and using standard C++ for a couple things. For one, I'm using auto to create an iterator. And then later on, I use the auto and ranged for loop to pull out the data out of that container that I created. The container is a vector of ints. So let's go take a look at what we do in the sorter portion of the function to create this functionality. So to generate the numbers, I just create a random device. And again, this is the one that is sort of the all-in-one, easy-to-use random number generator. Pardon me. And I'm calling its function operator to ask it for a random number. So pretty basic there. And then when I go to sort the numbers, I call the sort function. And so this is where I use a Lambda expression, because normally a sort function asks me for a pointer to a function that implements some kind of comparison. It takes two types or two variables of the same type and compares them and returns a bool. So you see the syntax here where I am saying begin the Lambda expression, and I can use something like the reference operator to say, capture by reference, pass it the two argument types I want, and do something with them. Now, here, I would normally specify the return type. But since it knows that it can infer a Boolean because I'm doing a comparison, I don't have to provide that in this particular anonymous function. So again, just some basic examples of C++11. There's a lot to explore. This is a very compliant compiler, one of the best in the industry right now. And so I encourage you to spend some time with the new compiler and exploring these new functions, and let's talk about them together. And as a C++ community, I really enjoy geeking out, if you will, on language and library features in particular. So at this point, Anders, I think I'm ready to take some questions.
Questions keep coming in, and we've got lots of questions here. So if you take the microphone over there. With the issue of portability being important, is it a long way off that we have a C++11 compliant 32-bit compiler so that we can use all the new cool features in both builds?
As I mentioned yesterday, it definitely is our intention to backport this toolchain to 32-bit Windows. In terms of time frame, we don't have any information to share today, but I will talk about our priorities. Our priorities after delivering the 64-bit toolchain is to deliver ARM compilers for iOS and Android. And this architecture is also being used by the Delphi language to create ARM binaries. So that's our priority right now. With that said, it is also a high priority to backport this to 32-bit, but we don't have a release date to share with you yet.
Okay, so that answers one of Samwise questions as well. That was a duplicate. Yes, eventually we'll port that back. That's on the roadmap. Will the C++ Builder 64-bit compiler for Windows also be available for Mac OS X?
Eventually, yes. Today we have our 32-bit based on BCC32 compiler for Windows and for Mac, and ultimately all those compilers will be based on this same architecture.
Great. Now for iOS and Android C++ support in Mobile Studio, will you use the new C++11 compiler?
Yes, we will. As I mentioned yesterday as well, and I didn't talk about it today, but this is a new architecture. This is the first release of this new architecture, so this is the first target platform that we've implemented. And then as we go down the line, again, priorities right now are iOS and Android. We will be using this architecture, and the C++11 compiler will be the toolchain that we deliver mobile on, and again, eventually future platforms, even backported platforms.
What version of Clang are you based on?
I am drawing a blank, but I believe it's 3.1.
3.1.
Yeah.
That's what I thought as well, yeah. I wanted to use C++ 11 for visualization with C++ Builder. Do you have any examples on using tuples on EDN? I couldn't find any.
I don't know if we have any on EDN yet, but I'll write an article about it. Tuples are actually really straightforward to use. You spend 10 minutes with it in the new compiler, you can figure it out pretty quickly how to work with them. It's just like setting up any type of a container class, template-based container class. So if you're comfortable using templates and container classes, then I think you'll find tuples are really straightforward to use.
Okay, so J2 will blog about that. I also did a impromptu 3D visualization math viz yesterday that will be available for replay shortly as well with all the other replays.
Oh, cool.
I didn't use any tuples or any C++ 11 features. I purely ported a Delphi FireMonkey demo to C++ Builder, and I showed it in 32-bit, 64-bit, and on the Mac.
That'd be a fun one to move to C++ 11. Good example to use, I think.
Yeah. So what is the upgrade path and update price model based on XE3 for the upcoming C++ Builder roadmap? Features like Android. For Android support, ARM, etc. To use the new. So going forward, can you talk a little bit about the roadmap and how to get different features or what the added cost will be and things like that?
To some extent, I can. We did publish a roadmap specifically around iOS. And basically, for the iOS compiler that we're working on, we are going to make that available to customers who have maintenance contracts or software assurance contracts with us. How we go to market with iOS and Android, we haven't made a final determination, nor have we put together any pricing. So at this point, it's a little premature to talk about exactly how we go to market with these additional features. But for today, if you buy C++ Builder XE3, you do get this 64-bit compiler.
Okay, I'm going to grab presentation rights back here and share the roadmap article. So edn.embarcadero.com, article 42544. I can post that in here as well. That's the mobile roadmap article on EDN right here. Send that. So there's the URL for you guys. And at the end here, we have the roadmap, and you can figure out where you fit in depending on what edition you have, and whether it's a low-cost iOS add-on or whether software assurance applies, etc., for both iOS and Android here. On the roadmap. Let's see. By the way, the C++ Builder XE3 and Rad Studio XE3 trial editions have been updated to include the new C++ Builder 64-bit compiler for Windows. Yes.
Yes, go play with it.
Thank you very much. Mr. Samwise, is there any feature?
Is that his real name?
That is his real name, Samwise
Awesome.
Gamgee. Yeah, absolutely.
I've been reading Lord of the Rings again, and love his character.
There you go. Yeah, I can't believe he's on all these webinars and CodeRage. This is fantastic. It's pretty cool. So maybe there's some hidden C++ Builder features in the movie. We'll see.
Where's Frodo?
Yeah, exactly. Is there any feature of C++ 11 that has not been implemented for this release?
Well, yes, there are a few features based on the level we're at with the Clang front end. As well as the STL. So there are a few. One that comes to mind is the new threading library. So this is the futures and promise syntax of the threading library. And the reason why that hasn't been delivered yet is because we need to make it compatible with the Delphi threading model. So that's going to take a little extra work to deliver that particular feature. But for the most part, this is probably the most or one of the most compliant C++ 11 compilers out there in the market today.
Is there any way to force a package build to be 64-bit? Yeah, you just target 64-bit, add the target platform, right?
Well, that's it's true for Delphi. Actually, that's something that we're going to be delivering in an update, as it had a few bugs that we wanted to fix. So it's not available in this initial release, but will be addressed pretty soon.
So will come in a patch.
Yep.
ETA?
No ETA.
Okay.
But it's high priority.
Okay, so real soon now?
Trademark.
Yeah, exactly. Okay, any more questions? Give it a shot, put in some questions. Other than that, we are at the top of the hour.
And I apologize for the technical issues this morning. That spinning beach ball is still spinning in my head. But, I hope you guys enjoyed this real quick discussion of C++11. Again, there's a lot more features to explore. So I'm having a great time playing with it and trying things out. And I hope you do as well.
There's a future question as well. Is C++11 going to be essential for WinRT development going forward?
Essential, I wouldn't go that far. I'd say that Microsoft actually has a pretty compliant compiler themselves. Not as compliant as this tool chain, but they also do use their own extensions for certain features. So I don't think it's essential, but certainly if you're writing compatible code between our compiler and theirs, then you'll definitely want to use standard features and C++11 features between them. There's actually a couple of good websites too that highlight the level of compatibility with the language in MSVC versus various versions of Clang as well.
All right. Thanks again, JT, for that presentation.
You're welcome.